Right now, at this exact moment, while you are lying here in the dark, there are scientists in Chile, in Hawaii, in orbit above the atmosphere, pointing instruments at distant stars and asking a question that has haunted the human species since the first of us looked up. Is there another world out there like ours? Not a gas giant, not a frozen rock, not a burning hellscape of acid and pressure. A world with liquid water on its surface, with a sky, with seasons, with the possibility, even the remote, fragile, terrifying possibility of life. And here is the question this video is really asking. Not just whether such a world exists. We will get to that, and the answer will disturb you. The real question is this: what happens on the day we find it? What happens to science, to religion, to politics, to the way you look at the sky when you walk outside at night? What happens to the human species when we are no longer alone in the universe? Not in theory, not in philosophy, but in fact, you are about to find out. All of it. From the first telescope pointed at the right star to the moment a government stands at a podium and tells the world what we found. If the dark has ever made you feel small and strange and curious, this is the channel for you. Subscribe to Sleepy Cosmos, and then come with me. We begin now. To understand how close we are to finding another Earth, and to understand what it would actually mean, we have to start somewhere that might feel too familiar, too ordinary. We have to start with the night sky that our ancestors stared at and had no framework to understand. For most of human history, the stars were not suns. They were lights, fixed, eternal, decorative. The ceiling of a cosmic room in which Earth was the floor. The entire observable universe, as far as any person alive before the 17th century understood it, was a tidy arrangement with us at the center and everything else orbiting around us. This was not superstition. It was observation. The stars appeared to rotate around the Earth once every 24 hours. The sun rose and set. The planets moved against the fixed background of stars. Everything about the visible sky suggested that Earth was the hub, the anchor, the important one. And then everything began to break apart. Not quickly, not dramatically. In slow, reluctant steps, pulled forward by mathematics and observation and the accumulated courage of people willing to say that what they were seeing contradicted what everyone believed. In 1543, Nicholas Copernicus published a model that placed the sun at the center of the solar system. He was afraid of the reaction and reportedly only agreed to publish it when he was close to death. He was right to be cautious. The idea that Earth was not the center of the cosmos was received by many as an assault on human dignity, on the meaning of creation, on the structure of theology. In 1610, Galileo pointed a crude telescope at Jupiter and saw 4 small lights orbiting it. Not Earth. Moons of another world. Proof that the universe did not organize itself around us. He was placed under house arrest by the Inquisition and spent the last years of his life confined under orders not to write or speak about the cosmos. In 1687, Isaac Newton gave us the mathematics that unified the motion of the planets with the fall of an apple. The same gravity, the same rules, everywhere. The universe was a machine, and its machines operated identically. The rules of physics were not global, they were universal. That word, universal, had a weight that would only become clear much later. Because if the laws of physics are the same everywhere, and if those laws allowed a rocky, water-covered, atmosphere-wrapped planet to form here, then those same laws would allow the same thing to happen anywhere else that similar conditions arose. The question was no longer whether another Earth was possible. The question became, how many are there? For centuries, that question had no empirical foundation. We could imagine other worlds. We could do the mathematics of probability. We could argue philosophically. But we could not point to a single confirmed planet orbiting any star other than our own sun. That changed on October 6th, 1995. The place was a conference room in Florence, Italy. The occasion was a scientific meeting on stellar astrophysics. Two Swiss astronomers, Michel Mayer and Didier Queloz, stood before their colleagues and announced that they had found a planet, not in our solar system, around another star. The star was 51 Pegasi, a yellow dwarf star roughly similar to our own sun, located about 50 light-years away. And orbiting it was a planet, a giant, massive, Jupiter-like world, but orbiting so close to its star that a year on its surface lasted only 4 Earth days. They had found it not by seeing it. The planet was invisible, completely swamped by the light of its star, but by detecting its gravitational tug. When a massive planet orbits a star, the star does not sit perfectly still. It wobbles very slightly, pulled first toward the planet and then away as the orbit proceeds. This wobble produces a tiny shift in the star's light, a Doppler shift, a stretching and compressing of the wavelengths that a sufficiently sensitive instrument can detect. Mayer and Queloz had that instrument. They had been measuring the wobble of 51 Pegasi, and the wobble was unambiguous. Something massive was pulling on that star with a period of 4.2 days. A planet around another sun. Confirmed. Mayer and Queloz won the Nobel Prize in Physics in 2019. And the floodgates opened. Within a decade, dozens of planets had been found around other stars. All of them giants, all of them detected through the wobble method or through a related technique, watching for the tiny dimming of a star's light when a planet passed in front of it, blocking a small fraction of the starlight like a fly walking across a searchlight. But these were not Earths. They were massive, gaseous, hot, inhospitable. The technology of the time was not sensitive enough to detect a small, rocky world like ours. The signal from an Earth-sized planet was too faint, the wobble too small, the dimming too slight. To find another Earth, you needed something better. You needed something like the Kepler Space Telescope. Launched in March 2009, the Kepler telescope was designed for a single, focused purpose. It stared at a small patch of sky containing approximately 150,000 stars, and it watched for the transit signal. The tiny periodic dimming that occurs when a planet passes between its star and the telescope. Earth, transiting in front of the sun as seen from outside, would cause the sun's brightness to drop by about 0.0084%. That is not a typo. Not even 1/100th of 1%. Kepler was built to detect variations in stellar brightness at that level repeatedly over the 9 years it operated. What it found was staggering. Planets were everywhere, not a few, not dozens, thousands. By the time Kepler's mission concluded, it had confirmed over 2,600 exoplanets and flagged thousands more as candidates. And those were just the ones whose orbital geometry happened to place them between their star and Kepler's line of sight. The transit method only works when a planet's orbit is tilted from our perspective, such that it passes in front of its star. For most planetary systems, the geometry is wrong. We would see nothing even if the system is full of planets. Statistical analyses of Kepler's data produced a number that became one of the most quoted in all of modern astronomy. The Milky Way galaxy contains, conservatively, tens of billions of Earth-sized planets in the habitable zones of their stars. Not millions. Billions. Tens of billions. When you absorb what that number actually means, when you really sit with it, it does something to you. the night sky you have looked at your entire life suddenly means something different. Those are not just stars. Every one of those points of light that you can see with the naked eye on a clear night is probably orbited by planets. Many of those planets are rocky. Some of them are the right size. Some of them are the right temperature. Some of them have liquid water. Kepler did not find another Earth, but it proved, statistically and beyond any reasonable scientific doubt, that another Earth almost certainly exists. Probably many of them. Probably an incomprehensible number of them spread across a galaxy that contains 400 billion stars. Now let us talk about the ones that are close, because there is a difference, an enormous, practically important, emotionally overwhelming difference between knowing that Earth-like planets exist somewhere in the galaxy and finding one near enough to actually study, near enough to look at directly, near enough to measure the composition of the atmosphere, to search for the chemical signatures of life, to know whether what we are looking at could be inhabited. And here is where the story stops being purely historical and becomes something urgently current. In October 2025, a team of researchers working with the Habitable Zone Planet Finder, an instrument attached to the Hobby Eberly telescope in Texas, announced the discovery of a planet called GJ251c, a super-Earth roughly 4 times the mass of our own planet, orbiting within the habitable zone of its host star at a distance of just 18 light-years from Earth. 18 light-years. To put that in terms that feel more real, the Milky Way galaxy is roughly 100,000 light-years in diameter. The observable universe stretches nearly 93 billion light-years in every direction, and this planet is 18 light-years away. In cosmic terms, it is in our backyard. If the galaxy were the size of North America, this planet would be about 30 meters from where you are sitting right now. The planet's discoverers called it the best candidate yet for direct imaging and atmospheric analysis. They pointed to the next generation of 30-meter class ground-based telescopes, instruments currently under construction in Chile and Hawaii, as tools that could, in the coming years, examine GJ251c's atmosphere directly and search for the chemical signatures that biology leaves behind. But GJ251c is not alone in the list of nearby candidates. In January 2025, astronomers confirmed a planet called HD 20794d, a world with roughly 6 times Earth's mass orbiting in the habitable zone of a sun-like star just 20 light-years from Earth. The discovery drew on over 2 decades of careful observation, and it was specifically highlighted by its discoverers as a target for the upcoming generation of life-hunting observatories. In January 2024, TESS, the Transiting Exoplanet Survey satellite, confirmed a super-Earth called TOI 715b, 1.5 times the width of Earth, orbiting in the conservative habitable zone of a red dwarf star about 137 light-years away. Its frequent transits, once every 19 days, make it an ideal target for the James Webb Space Telescope to examine for an atmosphere. And then there is the discovery that made headlines in August 2025 because it happened not somewhere distant, not around some faint red star hundreds of light-years away, but at the closest stellar system to our own. Alpha Centauri is 4 light-years from Earth. It is not 1 star, but 3. Alpha Centauri A, a near twin of our Sun. Alpha Centauri B, a slightly smaller companion. And Proxima Centauri, a faint red dwarf that already hosts 3 confirmed planets. Using the James Webb Space Telescope's mid-infrared instrument, with a coronagraphic mask blocking the blinding glare of the star itself, astronomers detected something. A faint point of light 10,000 times dimmer than Alpha Centauri A, sitting at roughly twice the distance between Earth and our Sun. A candidate planet in the habitable zone of the nearest Sun-like star in the entire sky. The object is tentatively identified as a Saturn mass gas giant, too large and gaseous to support life as we know it on its surface. But the scientific community reacted not with disappointment, but with something close to shock, because the implications extend beyond the candidate itself. If this world exists in that orbit, it may have moons, and a large moon orbiting a gas giant in a habitable zone, as science fiction has explored for decades, and as science is now beginning to take seriously, could have oceans, atmospheres, and conditions suitable for life. Moreover, the presence of this candidate tells us something about the planet-forming capacity of the Alpha Centauri system. If it has one planet, it likely has more. And among those additional worlds, smaller and rockier, and harder to detect, there may be an Earth. Literally next door. The researchers who made the detection published their findings in the Astrophysical Journal Letters in August 2025. They noted that the candidate's orbit would bring it back to a visible position by August 2026. If it reappears where the models predict, we will have confirmation of the nearest planet ever directly imaged. A world 4 light-years away, circling a star that is visible to the naked eye in the southern sky. Astronomers are watching. The world is waiting. But finding a planet is not finding another Earth. A planet is a location. An Earth is a story. To find another Earth, to actually earn the right to say that sentence with confidence, you need to look at the planet's atmosphere. You need to measure what it is made of. You need to search for the specific combination of gases that cannot coexist in a planet's air unless something biological is producing them. Those gases are called biosignatures. The concept is elegant and profound. Life, as it exists on Earth, is not passive. It is metabolically aggressive. It consumes and exhales and secretes and decomposes. And in doing so, it leaves a chemical stamp on the entire atmosphere of the planet it inhabits. You can look at Earth from space, not at its surface, just at its atmosphere, and know that something alive is here. Oxygen is the most obvious example. Earth's atmosphere is 21% oxygen. This is extraordinary. Oxygen is a highly reactive gas. It bonds eagerly with iron, silicon, carbon, and virtually every other common element. Left to itself, in a geologically active world, oxygen would be consumed within millions of years, locked up in oxides and carbonates. For oxygen to persist in an atmosphere at the levels we see on Earth, something must constantly be replenishing it. On Earth, that something is photosynthesis. Plants, algae, cyanobacteria. Billions of years of biological activity pumping oxygen into the air faster than geology can absorb it. The oxygen in the air you breathe right now was produced by life. All of it. Every molecule. But oxygen alone is not a definitive biosignature. There are abiotic processes, volcanic outgassing, photochemical reactions, that can produce modest amounts of oxygen in a planetary atmosphere without any biology. What makes the signature truly compelling is the combination. Earth's atmosphere contains oxygen and methane simultaneously. This is chemically impossible to maintain in equilibrium. Methane reacts with oxygen and is destroyed in about 10 years. For both to be present at the levels we observe, something must be continuously producing both. On Earth, that something is the simultaneous presence of photosynthetic and methanogenic life, plants making oxygen, microbes making methane. The two chemicals destroy each other. They cannot coexist without constant biological replenishment. Find those two gases together, in the atmosphere of another world, and you have found the strongest evidence science can currently provide that the planet is alive. But even this is not certainty. Astrobiologists are careful about this. Individual biosignatures can have false positives, abiotic explanations that produce the same signal. What you need is not one biosignature, but many. A pattern, a suite of chemical anomalies that, taken together, have no known abiotic explanation. The simultaneous presence of oxygen, methane, nitrous oxide, ozone, and a water vapor signature in proportions resembling Earth's. That is the bullseye. That is the signature that, if detected, would be the most significant scientific event in human history. And the telescopes capable of looking for exactly that signature are being built right now. The James Webb Space Telescope, already in orbit, already revolutionizing our understanding of the cosmos, can examine the atmospheres of planets transiting nearby stars. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching the telescope. Different gases absorb different wavelengths of light. By analyzing which wavelengths are missing from the transmitted starlight, scientists can read the atmosphere's composition like a fingerprint. Webb is already doing this for some planets. It has been examining the TRAPPIST-1 system, 7 Earth-sized planets orbiting an ultra-cool red dwarf about 39 light-years away, 3 of which orbit within the habitable zone. TRAPPIST-1e, one of the most closely watched worlds in astronomy, is being scrutinized for evidence of an atmosphere. Early data from JWST have hinted at the possible presence of methane in its spectrum, though scientists are cautious. The signal may also come from the star itself, and more observations are needed to be sure. But Webb was not designed primarily as a life-hunting telescope. It is powerful, and it is doing important work. But its mirror is 6.5 meters across. To detect the faint biosignature signals from an Earth-like planet around a Sun-like star, not a red dwarf, but a true solar analog, you need something larger, something more specifically engineered. That instrument is coming. NASA's Habitable Worlds Observatory, known as HWO, is the next flagship space telescope in the agency's planning, voted the highest priority for large space missions in the field's most recent decadal survey. HWO will be a space telescope with a mirror somewhere between 6 and 8 meters across, equipped with an advanced coronagraph so powerful it can block a star's light to 1/10,000,000th of its true brightness, allowing the faint reflected light from an orbiting Earth-like planet to be seen directly. Not as a transit signal, not as a wobble in the star's light, as an actual, direct image of the planet itself. A pale blue dot, or a pale orange dot, or whatever color it happens to be, hanging in the darkness beside its star. HWO's stated scientific goal is to examine at least 25 potentially habitable worlds and search for biosignatures in their atmospheres. 25 candidates looked at directly, their air chemistry measured, their surfaces indirectly characterized, their potential for life assessed. If the telescope is built and operates as designed, and there is no scientific reason it cannot, it will be capable of delivering a definitive answer to the question that has haunted the species for centuries. Are we alone? A formal start to HWO's development phases is expected in the early 2030s. If everything goes according to plan, it could be observing planets in the 2040s. The extremely large telescope, currently under construction in Chile's Atacama Desert, will be the largest ground-based telescope in history. A mirror 39 meters across, larger than the width of a 5-story building, capable of gathering light that dwarfs every instrument currently in existence. It is expected to begin operations in the late 2020s, and its design specifically prioritizes direct imaging and atmospheric characterization of nearby rocky planets. The European Space Agency's aerial mission, scheduled to launch in 2029, will conduct a large-scale survey of exoplanet atmospheres, examining approximately 1,000 planets in detail to build a statistical picture of what planetary atmospheres across the galaxy look like. The Nancy Grace Roman Space Telescope, scheduled to launch in May 2027, will hunt for thousands of new exoplanets and provide the technological stepping stones, including advanced coronagraph technology, that make HWO possible. The infrastructure for discovery is being assembled. The timeline is not centuries, it is decades. The answer to the most profound question in human history could arrive within the lifetime of people already alive today. Within your lifetime, possibly within the next 20 years. But this is the moment in the story where the science opens into something larger, where the technical question of detection expands into the human question of meaning. Because finding another Earth is not just a scientific event, it is a civilizational one. And the history of civilizational events, the moments when humanity's understanding of its place in reality has been fundamentally revised, tells us something about what that day would feel like. Something about what comes after. Consider what happened after Copernicus, after Galileo, after Darwin, after the first photographs of Earth from space. Each of these events followed a pattern: initial discovery, resistance, and controversy, gradual absorption into the cultural framework, and finally, a subtle but permanent shift in how the species understands itself. The photograph called Earthrise, taken by astronaut William Anders on December 24, 1968, during the Apollo 8 mission, showed Earth as a small, blue, fragile sphere rising above the barren grey horizon of the Moon. It is widely credited with igniting the modern environmental movement. People saw their planet from outside for the first time. They saw its isolation, its beauty, its smallness against the black. And something shifted. The philosopher and writer David Grinspoon has argued that humanity exists at a critical transition, from a species that merely inhabits a planet to a species that becomes consciously responsible for one. The Earthrise photograph nudged us, however slightly, towards the latter. What would the image of another Earth do? Not an artist's concept, not a computer rendering. An actual photograph taken by a real telescope of a real planet, showing, in its spectrum, in its chemical makeup, the unmistakable fingerprint of biology. We cannot know for certain, but we can reason carefully about the possibilities. There are scientific protocols in place for exactly this scenario. They have existed, in one form or another, since 1989, when the International Academy of Astronautics first drafted what is called the Declaration of Principles concerning activities following the detection of extraterrestrial intelligence. The declaration is not a secret document, it is a public commitment made by the scientific community about how they would behave in the event of a confirmed detection. And in October 2025, at the International Astronautical Congress in Sydney, the IAA voted on the most significant update to these protocols in their 36-year history. The core principle of the declaration is transparency. Any confirmed detection, whether it is biosignatures in a planetary atmosphere, a technosignature from an advanced civilization, or a radio signal that could only have been produced by intelligence, must be reported openly and immediately to the scientific community, to the public, to the Secretary-General of the United Nations. No suppression, no classified status, no controlled release through governments or intelligence agencies. The data belongs to all of humanity, and all of humanity is entitled to receive it. This commitment is meaningful precisely because of the pressure that would exist to violate it. The detection of life beyond Earth would be the most significant news story in human history. Governments would immediately recognize its geopolitical implications. Military establishments would see strategic value in controlling the information. Religious institutions would feel the destabilizing force of what the news implied. Intelligence services across every major nation would have both the capability and the institutional motivation to attempt to suppress or delay disclosure. Against all of that pressure, a group of scientists made a commitment, in public, on the record. Whether that commitment would hold under the actual weight of the actual moment is impossible to know with certainty. But the fact that the commitment was made, and updated as recently as 2025, tells us something about the character of the people who spend their lives searching for the answer. Let us imagine the moment, not as a thought experiment, but as a realistic scenario built from what we currently know about the science, the detection process, and the human systems that would surround it. The year is 2041. A telescope that has been operating for 3 years, somewhere between the capabilities of the Extremely Large Telescope and the Habitable Worlds Observatory, has been spending observation time on a planet catalogued as a high-priority target. The planet orbits a G-type star, a solar twin in the confirmed habitable zone. It has been known for years. It is roughly Earth-sized. It has a stable orbit. It has passed every preliminary filter. The telescope's spectrograph begins accumulating data on the planet's atmosphere. The first night's data is inconclusive. The second night produces a signal that makes the graduate student analyzing the data pause. The third night confirms the signal is real. By the end of a week of observations, the pattern is unmistakable. Oxygen, methane, nitrous oxide, ozone, water vapor, all of them simultaneously. All of them at levels that have no known abiotic explanation. The team lead, a professor probably, calls a meeting. They look at the data together. They run every possible check, every alternative explanation, every instrumental artifact, every known false positive. They work for weeks before anyone outside the immediate team hears a word. When they are satisfied, when they have exhausted every skeptical interpretation, they share the data with a small circle of trusted colleagues at other institutions, bound by an informal embargo. Those colleagues run their own analyses. The data holds. Now the protocols kick in. The team prepares a paper for peer review. But before submission, per the Declaration of Principles, they notify the Secretary of their National Astronomical Organization, who notifies the International Astronomical Union, who notifies the Secretary General of the United Nations. The United Nations notification happens on a Tuesday. By Friday, the information has reached the relevant offices of every permanent member of the Security Council. Governments begin making decisions, in quiet, about how to manage what is coming. The paper goes into peer review. Peer review, even expedited, takes weeks. During those weeks, rumors begin to circulate in the physics community. Not specific, just a feeling, a tone in emails, a specific name coming up in whispered conversations at conferences. The paper is accepted. The journal notifies its media contacts 24 hours before publication. The discovery team gives a single press conference, streamed globally, at a carefully chosen time. At that press conference, a scientist, wearing what looks like an ordinary blazer, nervous, visibly moved, looks into the cameras and says words that will be quoted for as long as the human species exists. We have found evidence of life beyond Earth. What happens next is where this stops being science and starts being something else entirely. In the 24 hours following that announcement, social media does not amplify the news. It becomes an undifferentiated flood of noise that makes the news harder, not easier to understand. Every conspiracy theory about government suppression, every religious interpretation, every ideological framework that had been waiting for exactly this moment immediately rushes to claim the discovery for its own narrative. A prominent political figure in a major democracy issues a statement calling the discovery a hoax. Another government announces it will form an independent commission to verify the claim before accepting it as true. A third government, in a country where the ruling ideology has theological dimensions, goes silent for 18 hours before issuing a statement so carefully worded, it manages to say essentially nothing. Meanwhile, in a city in South America, a group of people gathers spontaneously in a public square. They are not protesting. They are not celebrating. They are just standing together, looking at the sky. This happens in 17 other cities within 6 hours. Religious leaders issue statements, and the statements are more varied than many expect. Some denominations interpret the discovery as confirmation of divine abundance. If God created one world with life, why not many? Some interpret it as a call for expanded humility and stewardship. Some interpret it as a challenge to the foundations of their theology and say so honestly. A small number retreat into denial. Philosophers who have spent careers thinking about exactly this moment publish short, urgent essays. The question they grapple with is deceptively simple. Does the existence of life elsewhere change the moral status of life here? If we are not unique, if life is a planetary phenomenon rather than a cosmic, miracle specific to Earth, does that make life more valuable because it proves the universe tends toward its creation? Or does it make life less precious because it removes the argument for our singular importance? There is no consensus. There will not be one. And here is where the second layer of the question opens, because detecting another Earth, even confirming life on another Earth, tells us only that life exists there. It does not tell us whether that life has a mind. The biosignatures that astronomers are searching for, oxygen, methane, their combinations, are the signatures of microbial life. Bacteria, algae, organisms that have existed on Earth for over 3.5 billion years, and which would have been detectable by a sufficiently advanced telescope almost from the moment they appeared. Multicellular life is much more recent on Earth. The Cambrian explosion, the rapid diversification of complex animal life, occurred roughly 540 million years ago. Vertebrates have been around for about 500 million years. Mammals for about 200 million. The genus Homo for about 3 million. Modern humans for 300,000. In geological time, we arrived almost yesterday. If life is relatively common in the universe, but complex life is rare, then the first planet we detect biosignatures on is vastly more likely to be covered in microbial mats than in something that could look back at the telescope. It is more likely to look like Earth 3 billion years ago than Earth today. And this fact carries its own extraordinary weight, because it means that in detecting another Earth, we would almost certainly be looking at a moment in the past, a window into the history of life itself. A planet that could, over the next billion years, if conditions remain stable, develop complexity, diversity, possibly awareness. We would be looking at a world in progress, a story midway through its telling, and we would have found it at exactly the moment when we have the instruments to see it. Not a billion years ago when we lacked the technology, not a billion years hence when it might be too late. The timing would not be accidental. It could not be. The universe has a deep, disturbing tendency to produce the conditions for complexity precisely when complexity is present to observe it. But what if we find something more? What if the biosignature we detect is not oxygen and methane, the signal of simple biology, but something that has no natural explanation at all? What if the spectrum of the atmosphere contains a gas that should not exist in nature? What if, in the light from a nearby star, we detect a pattern that is too regular, too structured to be geological or biological? This is the territory of the techno-signature, the signature not of life, but of technology, the signal not of a biosphere, but of a civilization. Researchers at the SETI Institute published a study in early 2025 that asked a striking question. If an alien civilization with technology similar to ours were looking at Earth from another star system, what would they see? The answer, which was published in the Astronomical Journal, is that Earth is already leaking our presence into the cosmos. The former Arecibo Observatory's radar emissions were detectable, in theory, from as far as 12,000 light-years away. Atmospheric nitrogen dioxide, pollutant industrial processes that does not occur naturally at Earth's current levels. It's becoming more detectable as our instruments improve. City lights, heat islands from urban areas, the orbital signature of our satellite networks. All of these could, with sufficiently advanced instruments, reveal the presence of a technological civilization to an observer elsewhere in the galaxy. If we can imagine that, then we must face the logical reciprocal. If a technological civilization exists on another world, and if that civilization has been producing its own equivalent pollution and radio emissions for even a fraction of the time humans have been doing so, then it too is leaking its presence, and we might be able to detect it. The search for extraterrestrial intelligence, SETI, has been listening for exactly this kind of signal since 1960. That year, a young astronomer named Frank Drake sat at the controls of an 85-foot radio telescope at the Green Bank Observatory in West Virginia on a cold April morning and began a systematic search of two nearby sun-like stars for radio signals that did not come from any natural source. He called the project Project Ozma. He found nothing, but the search did not end. It expanded. It became the foundation of a scientific discipline. Dozens of subsequent searches using increasingly powerful instruments, scanning wider patches of sky, listening across wider ranges of frequency, looking for the signal that would prove the silence was not total. In 1977, a researcher at Ohio State University named Jerry Amon was reviewing data from a radio telescope survey when he saw something extraordinary. A strong, narrowband radio signal at exactly the frequency predicted to be optimal for interstellar communication. The frequency of hydrogen, the most abundant element in the universe. The signal lasted for 72 seconds and then was gone. Amon circled it on the printout and wrote a single word in the margin. Wow. The wow signal has never been explained. It has never been detected again. It remains the most compelling candidate signal in the history of Radio SETI. A data point that is consistent with the hypothesis of an artificial transmission, but that cannot be confirmed because it was never repeated. Since 1977, we have been listening. Nothing else like it has been detected, but the listening is getting better. In 2015, the Breakthrough Listen Initiative was announced, a $100 million 10-year program to conduct the most comprehensive radio and optical SETI search in history, using some of the most powerful telescopes on Earth. Breakthrough Listen has been scanning millions of stars, covering a wider range of frequencies than any previous program, and processing the data with artificial intelligence systems that can identify candidate signals that human analysts would miss. As of March 2026, Breakthrough Listen has not found a confirmed detection, but it has produced a finding that is itself significant. The galaxy is quieter than some early estimates suggested. If technological civilizations are common, they are either not broadcasting in ways we can detect, or they are more distant than our searches have so far reached, or they are communicating in ways, narrow laser pulses, quantum channels, gravitational wave modulations, that we are not yet looking for. The silence is not proof of absence. It is data. And like all data, it constrains the hypotheses. There is one hypothesis about the silence that is darker than the others, more unsettling. It was first articulated clearly by the physicist Enrico Fermi in 1950 in a casual conversation during lunch at Los Alamos National Laboratory. The argument is simple. The galaxy is 13.6 billion years old. The Sun is 4.6 billion years old. Stars older than the Sun with potentially habitable planets have had billions of years more time to develop technological civilizations. Even at speeds far below the speed of light, a civilization with the motivation and technology to do so could colonize the entire galaxy in a few tens of millions of years. By statistical expectation, this process should have started long ago. Probes, signals, colonies, some trace of extraterrestrial civilization should be everywhere, detectable, obvious, and yet nothing. Where is everybody? This is the Fermi paradox, and it has generated a library of proposed solutions. Perhaps civilizations develop, reach a certain level of complexity, and then destroy themselves through war, through ecological collapse, through runaway technology that outpaces wisdom. Perhaps the critical event, the evolutionary step that produces intelligence, is so astronomically improbable that it has only happened once, here despite billions of chances. Perhaps civilizations reach a technological level at which physical colonization becomes irrelevant. They upload themselves into digital substrates, or they withdraw to virtual realities, or they find ways to manipulate reality at a level we cannot currently conceive. Perhaps they are here and we cannot recognize them because we do not know what to look for. Each of these proposed solutions has a name and a literature. The Great Filter, the Rare Earth Hypothesis, the Zoo Hypothesis, the Dark Forest. The Dark Forest Hypothesis, articulated in its most chilling form by the Chinese science fiction writer Liu Cixin, proposes that the universe is full of civilizations that remain deliberately silent because revealing your existence in a universe of potentially hostile, resource-competing entities is suicidal. Every civilization discovers this eventually. The result is a cosmic silence maintained not by absence, but by terror. A forest filled with hunters who dare not make a sound. This hypothesis is not mainstream science. It is speculative, but it is intellectually serious, and the scientists who think about the Fermi paradox take it seriously as a possibility. Because here is what it implies. If we detect another Earth tomorrow, if we find biosignatures, if we confirm life, if we begin to narrow the search for signals that might indicate intelligence, we might also be finding something we were not supposed to find. We might be observing a world that has not yet learned to be quiet. A world in progress in a cosmos where being in progress is dangerous. We might be looking at ourselves from the outside. The philosophical weight of the second Earth is not reducible to biology or astrophysics. It threads through every human framework that attempts to answer the question of why we are here and what our existence means. Religious traditions across the globe have grappled with the question of extraterrestrial life for centuries, often more openly than popular perception suggests. The Vatican's astronomer, Brother Guy Consolmagno, has written extensively about how the discovery of life beyond Earth would be theologically unproblematic for mainstream Catholic theology. If anything, it would expand the understanding of divine creative abundance. Islam's theological framework, with its explicit acknowledgement of the possibility of other worlds in creation, has a ready conceptual scaffold for the discovery. Judaism, in its tradition of questioning and reinterpreting, has long had minority voices arguing that the universe's scale demands life's universality. The traditions that would face the greatest challenge are those that locate the uniqueness of the human soul, the singularity of the divine relationship with this species, at the center of their theological architecture. If that uniqueness is structural, if the entire edifice of the tradition depends on humans being the only creatures in the cosmos who matter, then the discovery of another Earth is not an expansion of the theology, it is a rupture. But theology has survived ruptures before. It absorbed Copernicus. It absorbed Darwin. Each time after the initial shock, new interpretations emerged that preserved the emotional and ethical core of the tradition, while releasing the cosmological framework that turned out to be wrong. It would happen again. What would not recover so easily is the psychological assumption of cosmic centrality that is so embedded in human experience, it mostly goes unexamined. Not the religious claim that we are unique, the simpler, more pervasive feeling. The quiet background assumption that the universe, the specific universe, we inhabit with its specific laws and its specific arrangement of matter, is in some sense organized around us. That our consciousness, our suffering, our love, our death is what the cosmos is ultimately about. That assumption would not survive the second Earth. And in its place, slowly, over years and decades, through the gradual cultural work of processing what the discovery means, something different might grow, something more accurate, more humble, more honest. There is a concept in philosophy called the overview effect. It was identified and named by the writer Frank White, who interviewed astronauts about the psychological impact of seeing Earth from space. Nearly all of them described the same experience, a shift in perspective so fundamental it was difficult to put into words. A sense that national borders, cultural conflicts, political divisions were not just temporary obstacles to human cooperation, but were, from the vantage of space, revealed to be almost incomprehensibly small compared to the shared vulnerability of the thin blue shell of atmosphere that separates everything they knew from the void. The first photographs of Earth from space did not produce world peace. They did not eliminate nationalism or tribalism or the territorial impulses that drive conflict, but they introduced a new way of seeing the species from outside that has never entirely left the cultural imagination. It seeded an idea that has not yet fully bloomed. The discovery of another Earth would be a different kind of overview effect. Not the experience of seeing our world from outside, but the experience of seeing our world from beside, from next to another world that is also filled with life. The experience of placing Earth in a category. No longer the world, one of the worlds. The shift from the definite article to the indefinite article. From the world to a world. From the Earth to an Earth. This is not a small grammatical change. It is a revolution in self-understanding. It is the difference between being the protagonist and being a character. And from that shift, from that moment of revised self-understanding, specific, practical consequences flow. The most immediate is the question of what we do. If we find a planet with life, the scientific impulse will be immediate and overwhelming. Study it, understand it, learn everything we can about the nature of this other biology, this other chemistry, this other evolutionary experiment. Does it use DNA? Does it use the same amino acids? Does it operate on the same biochemical principles, suggesting that life everywhere converges on the same solutions? Or is it fundamentally different, a biology built on a different architecture, answering the same evolutionary pressures with completely alien solutions? This is not an idle question. The answer would tell us something foundational about the nature of life itself. It would tell us whether life is a universal law, a thermodynamic attractor, an inevitable outcome of certain chemistry in certain conditions, or whether it is a historical accident, a contingency, something that happened to arise here and there but has no deeper necessity. If life is a law, then the universe is teeming. Every world in the habitable zone of a stable star that has had 1 billion years of liquid water is alive, or was alive, or will be alive. Life is as inevitable as stars. If life is an accident, then each instance of it is a miracle, a fragile, improbable, unrepeatable event. And the response we owe it, both the life on the other world and the life here, is proportional to that rarity. Either way, the ethical implications are severe. What would it mean to travel to another Earth? The nearest confirmed habitable planet candidates are, at the moment, between 4 and 20 light-years away. Even the closest, a world in the Alpha Centauri system, if it turns out to be rocky and habitable, is 4 light-years away. That is approximately 40 trillion kilometers. At the speed of the fastest spacecraft ever launched by humanity, Voyager 1, which is traveling at about 17 kilometers per second, it would take approximately 75,000 years to cover that distance. We are not going in our lifetimes. We are not going in our grandchildren's lifetimes or their grandchildren's lifetimes. Not with any technology that currently exists or that we currently know how to build. But the question is worth asking anyway, because thinking about how we might eventually get there tells us something about what we might become. Breakthrough Starshot was an initiative announced in 2016, backed initially by Stephen Hawking and Russian entrepreneur Yuri Milner, to develop a means of sending a tiny spacecraft, a few grams, a small chip of silicon carrying cameras and sensors, to Alpha Centauri at 20% of the speed of light, using a ground-based laser array to push a gossamer light sail. At that speed, the journey would take 20 years. The chip would arrive. It would image the system. It would send back what it sees at the speed of light, taking another 4 years to reach us. 24 years from launch to first image. That is within a human lifetime. Breakthrough Starshot was reported to be on indefinite hold as of September 2025, having spent only a fraction of its initial funding. The engineering challenges: building a laser array of 100 gigawatts of coherent power, creating a light sail that can survive the acceleration and the interstellar medium, miniaturizing functional sensors to gram scale, remain formidable. But the physics is sound. None of the obstacles are violations of known natural law. They are engineering challenges. Expensive, difficult, multi-decade engineering challenges. A chip the size of a postage stamp arriving at Alpha Centauri, carrying cameras and spectrometers, sending back photographs of a living world. This is a plausible scenario for the 22nd century, but before the ships, before any physical contact, before any probe arrives, there is a question that the discovery itself immediately raises. A question so large that every national government, Every international organization and every individual on the planet would have to grapple with it. If we find life on another world, what do our obligations to that life look like? This is a question that science does not answer. Science can tell us whether something is alive. It cannot tell us whether it has interests, whether those interests matter, whether our presence in its sky, or eventually on its surface, constitutes a violation of something fundamental. The ethical framework humans currently use for life on Earth is already inadequate for its purpose. We have not succeeded in protecting the life forms on our own planet. We have driven species to extinction at a rate that scientists are calling the sixth mass extinction event in Earth's history. We have polluted and cleared and consumed with a thoroughness that has visibly altered the chemistry and climate of the only biosphere we know. Now, imagine adding a second biosphere to that picture. A world of alien life, fragile in ways we do not yet understand, subject to pressures we cannot predict, watched over by a species that has demonstrated on its own planet a troubling tendency to treat life as a resource. The question of what we owe another Earth's inhabitants, even if those inhabitants are nothing more complex than microbial mats, photosynthesizing films of single cells, would not be a scientific question. It would be a moral one, a political one, a deeply, irresolvably contested one. Some would argue that the life on another world has no claims on us, that rights and obligations are human concepts, applicable only within human frameworks, and that microbial life on another planet is no more deserving of our ethical consideration than a rock. Others would argue that life, wherever it exists, has inherent value that precedes and supersedes any human framework, and that our arrival in another world's biosphere, even as observers, even remotely, is already a form of intrusion that carries responsibilities. Neither position will win. Both will be represented in every parliament, every university seminar, every late-night conversation that follows the discovery. What will emerge slowly, imperfectly, through the messy process of international negotiation and cultural argument and scientific advocacy and philosophical debate will be something like a framework, not a perfect one, not an agreed one, but a working one. The kind of framework that allows the species to continue functioning in the face of a reality it was not built to fully comprehend. This is what we do. It is arguably the most human thing there is. There is a number that sits at the center of all of this, a number that was first proposed in 1961 by Frank Drake, the same astronomer who pointed a radio telescope at two nearby stars and listened. Drake was preparing for a scientific meeting at the Green Bank Observatory. The meeting's purpose was to bring together a small group of scientists to discuss the possibility of extraterrestrial intelligence. Drake wanted a way to organize the discussion, so he wrote an equation. The Drake equation is not a predictive tool. It is a framework for organizing ignorance. It expresses the number of technologically communicative civilizations currently in the Milky Way as the product of a series of factors: the rate of star formation, the fraction of stars that have planets, the fraction of planets that are habitable, the fraction of habitable planets where life actually develops, the fraction of life-bearing planets where intelligence develops, the fraction of intelligent civilizations that develop technology, and the average lifetime of such a civilization. Most of those factors were, in 1961, entirely unknown. The equation produced an answer that could be anything from one, just us, to millions. Since Drake wrote his equation, we have filled in several of the unknowns with real data. The rate of star formation in the Milky Way, well established. The fraction of stars with planets, approximately 1. Nearly every star has at least one planet. the fraction of planets that are in the habitable zone, now estimated in the billions. The fraction of habitable planets where life actually develops, unknown, still unknown. This is the most critical unknown in all of astrobiology, and the detection of another Earth would be the first real data point. Everything else, the intelligence fraction, the technology fraction, the civilization lifetime, remains deeply uncertain. But the first domino, the biological one, may be about to fall, and the implications cascade from there. If life is common, if the fraction of habitable planets that develop life is close to 1, suggesting that biology is an almost inevitable outcome of certain chemistry in certain conditions, then the Drake equation produces very large numbers. Thousands, possibly millions of civilizations may have existed in the Milky Way across its history. The Fermi paradox becomes more pressing because the silence of the sky is harder to explain if the galaxy is thick with life. If life is rare, if the fraction is close to 0, suggesting that despite billions of habitable worlds, the specific chemistry that gave rise to Earth's biosphere was extraordinarily unlikely. Then, we may be alone, not just unique, alone, the only living world in a galaxy of 400 billion stars. Both possibilities are terrifying in different ways. The first terrifies because of what it implies about the fate of civilizations. If life is everywhere but we see and hear nothing, something must be silencing the voices. Some filter must be removing civilizations from the active communication network of the galaxy before they can announce themselves. That filter might be behind us, the improbable transitions that led from chemistry to biology, from single cells to multicellular life, from life to intelligence, in which case we are among the lucky few who made it through. Or the filter might be ahead of us. Some transition that civilizations at our stage of development almost never survive. The second terrifies because of what it implies about meaning. If life is rare, if Earth is genuinely anomalous, a biological accident of staggering improbability in an otherwise sterile cosmos, then what we have here is not just precious. It is the only thing. All of the life that exists, everywhere in the entire observable universe, is here. On this small, fragile, profoundly mismanaged world, and we are in the process of destroying it. The last thing to say about the second Earth is the most personal. When that planet is found, and if the science is pointing us toward anything, it is pointing toward the strong likelihood that it will be found, probably before 2060, possibly within 2 decades. The person who first looks at the data and understands what they are seeing will be a human being sitting in front of a screen. They will probably not be famous. They will probably be a graduate student, or a postdoc, or a junior researcher, working late, running one more analysis on one more dataset. In a moderately funded laboratory at a university most people have never heard of. They will look at the numbers and see the pattern that cannot be explained by any known abiotic process. They will look again. And again. They will call over a colleague. And in that moment, before the protocols, before the press conferences, before the governments and the theologians and the philosophers and the social media platforms all rush to claim the discovery for their own frameworks, there will be just 2 people standing in a room looking at a screen. And one of them will say something like, "I think this is it." That moment will be irreversible. The world before and the world after will not be the same. Everything that humanity has ever built, believed, suffered, celebrated, and created has happened on one planet. Every love story, every war, every symphony, every genocide, every act of extraordinary courage, and every act of extraordinary cruelty. Every stargazing child and every dying elder and every scientist who stayed late to run one more analysis. all of it on one pale blue dot. And then the dot will have a companion, another world somewhere in the dark, also alive, also here. What we do with that knowledge will be the most important test this species has ever faced. Not a test of our intelligence, we are intelligent enough. Not a test of our technology. The technology is being built, a test of our wisdom, of our capacity to expand our circle of moral concern beyond the familiar, of our willingness to carry the weight of what we find with something approaching the responsibility it demands. We have not always passed such tests. We have often failed them catastrophically, with consequences that echoed through centuries. But we are still here, asking the question, building the telescopes, looking, and somewhere out there perhaps, around a star whose light reaches your eyes on a clear night if you know where to look, there is a world, spinning quietly, waiting to be found. Sleep well.